I wanted to talk a little bit more in depth about fundamental solutions for PDEs, but in order to do that, you really need to understand a bit more about the Dirac delta and convolutions. And in order to understand that, it really helps to talk a little bit about expected values and probability. So let's start there and work our way up to it. So the expected value of a function is the integral of that function with respect to the probability distribution P, where P is describing the probability distribution of the random variable or the random outcome x. So most of the time, this is written as the integral f of x px dx. And this part right here, this is called the probability density. Okay, so this is much better explained by an example. So suppose we let x, so this is a random variable, so it's the outcome of a random event, a numerically valued random event. So let x be the size of a tree. Whoops. Cut down, chosen at random, in a logging camp. So I'm from British Columbia, so I figured that would be a natural choice of example. Okay, and so suppose we let f of x be the dollar value of a tree of size x. So what does this look like? Well, it doesn't really matter. Suppose to make it sort of realistic, I'm going to say, well, it's probably some like vaguely increasing function of x, because bigger trees are worth more. You can get more boards out of them, right? Okay, so suppose that the tree cut down is chosen uniformly from a patch A. Okay, so what does that mean? So here's our map of what's going on out in forest country, and there's A. And so we're going to choose a tree uniformly at random from this patch. So if I look at the PDF for this thing, so then let's see, so it's going to be, so here's kind of the blob, and then we're not choosing from outside the blob, we're only choosing from inside the blob. So the height of our patch is maybe it's going to look something like this, and so we don't know what the what the area of A is, but the probability distribution for A is going to be 1 over the area of A if you're in there, and 0 if you're not in there, because we're not choosing trees from outside the patch. Okay, so uniform distribution, so that means it's all evenly distributed, so that means it's a constant height, and so that's why the graph over this region is flat. If I graph the vertical axis right here, then the height of that blue sheet that you're seeing right there, that's 1 over the area of A. So it's uniformly distributed. So remember, for probability, you need to have it be the case that your probability density function is non-negative, and that the integral of P is 1. That's what makes it a probability. Okay, so let's see then. So now, so if we choose a tree randomly from this patch, what's the expected dollar amount that it's going to be worth? Well, then the expected amount that we're choosing from A, so I'll put a little A there. So the dollar amount of the randomly chosen tree and so the randomly chosen tree chosen uniformly at random from A. Okay, so this is, according to our formula, f of x, p of a x dx, and our probability density function, oops, I already gave you the formula for that, so I don't need to write that again. And so then let's see, so then this is going to be 1 over the area of A. Actually, here, let me rewrite this slightly. Whoop. Okay, so it's going to be the integral over all of like R2, that's the whole space we're looking at, f of x, and then our function is this one that's going to be 1 over the area, or 0, depending on where we are, dx. And so I can split the integral into the integral over A, and in that the function has value 1 over area, plus the integral of the function over the complementary region R2 minus A, so that's everything outside the blue zone. And out here it has value 0. So that part is going to go away. And meanwhile, this first part here I can rewrite as 1 over the area of A, integral over A, f of x dx. And you recognize this from calculus class as the average value of f on A. And that's exactly what the expected value is. It's the average. Okay, so it's the average with respect to some sense. Here it's uniformly weighted. A different probability distribution might have weighted something sort of less uniformly, but oh well. Okay, so now suppose instead of choosing our tree from that big old patch, maybe we choose like a smaller patch somewhere inside it. Like suppose we take, this region right here. Okay, so we'll take that original one A, and let's call that one A1. And so now we've got some A2, and we've got that A2 is contained in A1. It's a subset of it. Okay, then the expected value that of the tree that we randomly choose at uniform from inside A2 is going to be, and then same calculation gives us 1 over area of A2 integral over A2 f of x dx. Okay, now the only thing is when we look back at the corresponding picture for what the PDF looks like, right? So now we've got some smaller region, and so we're going to have some smaller region up here. Okay, so this is supposed to be directly above that guy there. And so here's our little region A2. And we now move this up to being maybe up here somewhere for the area of A2. Okay, so key point, in order to maintain this condition that the integral of P is always equal to 1, if the region that you're looking at is smaller in area, then the value needs to be higher in order to have the total integral work out to be 1. Okay, so we could continue in this way. So we've got our original set A, which we're calling now A1, and then inside it we've got A2, and then inside that we could pick another one, and then we could keep on going like this, right? And so if we had, say, that the limit of these sets, say it just got smaller and smaller, shrunk down to a single point. So these guys are concentric to a single point. So this is when n goes to infinity. And if you've taken a set theory class, you'll recognize that this thing that I've written right here is actually a little bit nonsense. What I should have written is the limit as n goes to infinity of the intersection but if you haven't seen that before, then don't worry about it. Anyways, you get the idea. I'm just talking about a family of sets that gets smaller and smaller and smaller and smaller and smaller and smaller and smaller. It's nested, and somewhere down way at the middle in there is the point y, and it's the only thing that's in the very bottom there. So then if we look at the limit as n goes to infinity of the expected values of these things, then this is the limit as n goes to infinity of f of x pan x dx. And suppose we can take that limit inside so that we write this as limit pan of x dx. And then I want a name for this quantity inside the green parentheses right here. And so I'm going to call this delta y. So it's the Dirac mass or the Dirac delta at y. Okay. And then, but then it becomes clear that what's the expected value of f, given that you're restricting the place where you can choose your trees from to a single point? Well, it's going to be the value of the tree at that point. So this is just going to be exactly equal to f of y. And that's what the definition of the Dirac delta is. So it's defined by this integral. If you integrate f against dy, then you get f evaluated at that point.